Good evening, guys. This video I'm doing for S block. Actually, uh, we have done it in the offline classes. So the students who are doing the classes in online mode, this video is for them. So you should see the whole video. Okay, it is at first we'll make a video, uh, a detailed video. Okay, then we'll give some summary. Actually, both of them are important. So summary is also important. At first, we should see the detailed video. Maybe the video will not be, the whole topic will not be covered in the single video. That's why we should have to make another video. Okay. Now we are starting our topic here. This is actually for our S block. Okay. So this video you should see till the end. Okay. Okay. So actually, S block elements. Actually, S block elements is group one and group two. In group one, hydrogen is not included in S block. Actually, lithium, sodium, potassium, rubidium, and cesium. Fr is also not taken as it is radioactive in nature. Here, beryllium, magnesium, calcium, strontium, and barium. These are the S block elements. So, because their last electron enters in the S orbital. Actually, the topic is very much important. We'll first see the physical properties of the whole group, then we will see the chemical properties, then we will see individually some of the elements. So you should note down everything that I am giving here. Actually, this is not shortcut. Okay, this is a detailed explanation by scientific explanation, thermodynamic or kinetic parameters. Actually, this is not the shortcut. The shortcut will be the summary. Okay, but this is the most important part. If you are wanting to do good results in your JEE or NEET, you should know the details of your S block. Okay, so let us see. So at first, we will see the physical properties here. We will see first group one. Okay, physical properties, that is in a melting point. Melting point, you should know that lithium is the hardest among all of them. Cesium is liquid in room temperatures. So the melting point goes on decreasing while going from top to bottom. Actually, all of them has low melting point because they can't form strong metal bond or metallic bonds. So you can see in the D block, they have very high melting points because due to the presence of unpaired electrons, they will show strong metal bonding. But in case of the S block elements, they cannot form a strong metal bonding. That's why their melting points are very low. So lithium is the hardest among all of them, and it has the highest melting point. Cesium is liquid in the room temperature, so the melting point will decrease while going from top to bottom in the group. Next, you can see here, the next euro is density. Density is mass upon volume. While going down, the atomic mass increases, and the volume also increases. But what happens? You can see here, density is mass by volume. It is more significant, more prominent, or more significant So while going down, the density increases. So lithium is the lightest among all of them. However, potassium has a low density than your sodium due to the abnormal increase in size, increase in radius. I think the radius is 138 picometer. Okay, so it is not the it is the literature value. This may be wrong also. So lithium is the lightest among all of them. So this is why as lithium is lightest, this is very important. As lithium is the lightest, it can't be dipped in kerosene. So it is placed or dipped in paraffin. Okay, so that's why lithium is the lighter or lightest among all of them. That's why it cannot be dipped in kerosene as the density is very low. So it can be stored under paraffin or wrapped in paraffin. Okay, and that is about our density. Another physical property is that NCRT. You can see your we are going strictly according to our NCRT, page number 302. That is your dissolution in liquid ammonia. When you can see when alkali metals or earth metals are dissolved in ammonia, the solution becomes blue. Why this becomes blue? You can see here. When you can see sodium is given in ammonia, an ammoniated complex NaNH3 whole 6 plus 1 electron. This is known as free electron. Okay, this is known as free electron. Now this free electron is free to move. Okay, this free electron, whenever free electron, you can see that a higher number of sodium atoms whenever you take, a huge number of electrons will be released that will be in the free state. When light falls on them, they undergo excitation to the higher state. While jumping to their original position, it will release energy with high frequency, with a high frequency. The frequency is high. So you can see the bluish violet color in nature. Bluish violet color. This what happens actually. This electron is known as the ammoniated electron. Okay, whenever you dissolve sodium or potassium or lithium, etc., you can give it in ammonia or liquid ammonia. Actually, liquid ammonia can not be 7% of your ammonia. There is some amount of water. So what happens? Ammonia forms a complex. This is called ammoniated complex, and an electron is released during the process. So as the electron is released, it's a free electron. So whenever sunlight or any kind of energy falls on the electron, it undergo an extensive transition. Okay, whenever the extensive transition occurs, what happens? It absorbs the energy. While returning back to its original position, it will release the energy in the form of an electromagnetic spectrum. It falls in our visible region. As the gap is high, electron goes from low state to very high state. So the energy is high and the frequency is also high. That's why bluish violet color you can see. So this is very important. addition of addition further addition of metal gives a bronze color solution. Okay, but your lithium is actually exceptional. Okay, rest of the elements such as your sodium, potassium, etc., cesium, etc., can form amides, whereas lithium is the exceptional case. Lithium can form imide also. This is very, very, very important. Imide also, such as you can see potassium plus ammonia. This will produce KNH2, potassiumide. Na plus ammonia. This will produce NaNH2, sodamide. But lithium you can give in excess of ammonia. First you can form LiNH2. This can also be formed. But whenever you give excess of ammonia, then it will form Li2, sorry. When you can form excess of lithium, this can form Li2NH. This is known as the imide. Okay, imide. So lithium forms exceptionally imide. No other element in group 1 can form imide. So these are the most important points. Okay, these important points you should remember and write down. Imide formation. Rest of the elements is this, you can also say the anomalous property of your lithium. Okay. Next we are going to the reduction power or reducing power. Reducing power, it actually depends upon how easily an atom can lose one electron. So you can see the lithium has a very smaller size and cesium has a very larger size. Last electron is present here and last electron is present here. You can see the electron is far away. So it can be easily ejected. It can be easily ejected. So what happens? While it can be easily ejected, you are seeing it clearly, it should have the highest reducing power. But this is not true. Lithium has the highest reducing power, has the highest reducing power. This is because you can see here, while you see the electrochemical series, you will see that E0 of Li plus to Li is equal to minus 3.05 volt. This is known as the reduction potential. Or you can see this standard reduction potential. Standard means it is connected with your SHE. Okay, standard means whenever standard hydrogen electrode, we have seen the standard hydrogen electrode. Whenever standard hydrogen electrode is attached with the lithium, this will give you a standard reduction potential. That will be this one. So the reduction potential is minus 3.05. So as we know, lower the reduction potential, more the tendency to get oxidized and act as a good reducing agent. So you can see here, lithium will act as a very good reducing agent as this value is very low, or you can see the oxidation potential E0 of Li to Li plus. This is equal to plus 3.05 volt. Actually, this property is due to the, this can be explained by the very highly negative value of hydration enthalpy. That's why this factor, actually the hydration enthalpy, is directly responsible for the reducing power of lithium. Actually, it is the best reducing agent in the whole periodic table. You can see lithium has the most negative value in the periodic table. No one actually has the more negative value, than your lithium. So this is the best reducing agent. So after lithium, the reducing power trend is like that. The reducing power trend is like that. At first there is lithium, then your cesium, then your rubidium, then your potassium, then your sodium. It is the weakest reducing agent. So this is the strongest reducing agent in group 1. Actually, not in group 1. Actually, this is the strongest reducing agent in the whole periodic table. Strongest reducing agent in the whole periodic table. This is the weakest reducing agent in group 1. Okay. So all of them has higher reducing power. So they can't be produced in the presence of carbon reduction process or aluminium reduction process or aluminium reduction process. So you should remember they are produced by the electrolysis. So this is the way to prepare them by the electrolysis. None of the elements can be produced by the reduction process because they themselves are the better reducing agent than any of the substances present in the periodic table. Among them, lithium is the strongest reducing agent, and among them, in group 1, sodium is the most poor reducing agent. So this is the reduction power or reducing power of your or general trend of your group 1 elements. Okay. Next, you can see the reaction with water. You can see here. Reaction with water. What happens? You can see the reactivity of what with with water goes on increasing while going down the group. You can see lithium does not react with water under 0 degree or 273 Kelvin. Sodium react violently. Potassium, rubidium, cesium catches fire almost immediately. But 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 by the thermodynamics, Thermodynamics, by the thermodynamics, lithium should react with water violently, but it reacts mildly. This is very, 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 very important. Okay, this is very important, very important. So you can see here, by the thermodynamics, lithium should react violently. How this is possible? You can see, such as you can see, we are comparing with lithium and sodium. Okay, lithium and sodium. You can see lithium has a reduction potential Li plus to Li is equals to minus 3.05 volt. Here you can see E0 Na plus to Na is equal to minus 2.51 volt. Now what happens? You can see here. So as we see the Gibbs-Duhem equation, or you can make it as a collaboration of your Gibbs-Duhem equation and Nernst equation, delta G and Faraday's constant, minus n into F into E0 cell. You should find out in your in a redox or in your electrochemistry. You can see delta G is equal to minus n into F into E0 cell. Now you should put the value here for lithium. Delta G is equals to minus 1 into 96500 multiplied by minus 3.05. That is volt, sorry, that is joule. Here you can see delta G for sodium. This is for lithium. This is for sodium, minus 1 into 96500 multiplied by minus 2.51 kilojoule. So it is evident from the reaction that you are seeing that in here the higher amount of energy is released. So higher amount of energy released means the reaction should be violent, but in practice it is mild. This is because you can see, you should write down the point here. Actually, what happens? Actually, you see, lithium is the hardest among all of them, and amount of energy releases in higher quantity. There is no doubt of it, because according to thermodynamics, delta G is equal to minus n into F into E0 cell. So high amount of energy will be released during the process. But the problem is that as lithium is the hardest among all of them, maximum amount of energy that is released during the reaction with water will be spent to melt more and more number of lithium molecules or atoms. That's why the amount of energy that is released is very small. So the reaction becomes mild in nature. But actually, this is the kinetic explanation, not the thermodynamic explanation. According to thermodynamics, a high amount of energy will be released, but according to your kinetics, the maximum amount of energy will be spent to melt another lithium atom. So that's why the reaction is mild in nature. So you should remember this one, that the according to thermodynamics, the reaction of lithium with water should be violent in nature, but as it is hardest among all of them, that's why maximum energy is spent to melt the melt another atom. That's why a low amount of energy or a mild reaction appears. But actually, the energy is released in a very, very, very high quantity. Okay, so this is the this is the reaction with water. Actually, next you can also see the hydration enthalpy. This is also a physical property. Hydration enthalpy is a very important term. What is the hydration enthalpy? The amount of enthalpy change during dissolution of an element in water. what happens? Water form coordinate bond and produces a hydrated sphere. How this is possible? You can see lithium has a smaller size. H2O forms bond, forms bond, forms bond. You can see this is a hydrated sphere. This is a hydrated sphere. So what happens? Lithium has the most negative. It has the lithium has the most negative hydration enthalpy. So what happens as the hydration enthalpy is very, very negative, the sphere is stable. The hydrated sphere is stable and it is bulky also. And it is bulky also. So ionic mobility is very low. Ionic mobility is very, very low because it is bulkier in nature, because maximum number of water molecules come in the vicinity of lithium atom and can form a stable hydrated sphere, because the hydration enthalpy is very, very negative. As we know, in an exothermic reaction, whenever the heat will be released, the the sphere will become more and more stable. As the heat releases, the potential energy of the system decreases and the stability increases. So lithium, due to its high negative hydration enthalpy, it can form a stable hydrated sphere. As the hydrated sphere is very, very bulky in nature, it has a lower ionic mobility in water. You should remember the point. This is the most important point. Now, in case of, you can see the cesium, it has a larger size, so less hydration enthalpy. So you can see water, less number of water molecules will go on to meet the cesium, and the sphere is not so bulky. So it has a higher ionic mobility. It has a higher ionic mobility. So as you can see, at higher ionic mobility, so in aqueous phase, cesium has the highest ionic mobility, then your rubidium, then your potassium, then your sodium, then your lithium. But in fused condition or molten condition, lithium has the highest ionic mobility because there is no water here. Sodium, then potassium, then rubidium, then your cesium. This is the highest ionic mobility in the non-aqueous medium. This is in the non-aqueous medium. The above is your in the aqueous medium. So you should remember this one, that in the non-aqueous medium, lithium has the highest ionic mobility because of its lower size. But in case of aqueous medium, the lower ionic mobility of lithium is attributed to the fact that it can form a large stabilized hydrated sphere which is bulky in nature. That's why it cannot move in the solution in a higher speed. So this is the reason for your ionic mobility of different substances in your group 1. Then there is your flame test. Actually, what is flame test? It gives us a preliminary idea to identify the S block elements present in a salt or not. So how to do this? You can see sodium is your golden yellow. It will show the flame test. You dip a platinum wire in HCl concentrated, then touch the wire with salt, given salt, then apply in the flame. If you see these colors, that means these elements are present. Golden yellow means sodium, potassium means bluish violet, rubidium is red, cesium is blue or violet blue, calcium is brick red, strontium is crimson red, and barium is your apple green. So you should see these colors in the flame, and you could get a preliminary idea of these elements present in the salt or not. Okay, but these are not the confirmatory test. As an example, you can see here, you can see here when you can see barium, it shows an apple green color, but this is not the confirmatory test. This is not the confirmatory test. You can test confirmatory test. You can done it like such as barium chloride BaCl2 plus. You can add K2CrO4 potassium chromate. This is a group 4 reagent actually. So this will produce BaCrO4, a yellow PPT of barium chromate. So these are the confirmatory tests, as such as sodium can also be not be confirmed by the help of this flame test. You can do it by your potassium pyroantimonate, then it will give a sodium pyroantimonate white precipitate. Such as potassium can also be identified or confirmed by the sodium cobalt nitrate. This will give a yellow precipitate of potassium cobalt nitrate. So these flame tests will give you a preliminary idea, but not actually the whole idea or the confirmatory tests. Okay, this cannot be used as a confirmatory test. These are the tests to identify or preliminary and identify the element is present or not. Okay, the confirmatory test in the practical chemistry is different from the flame test. Okay, next we'll see the reaction with air. Okay, air actually contains two types of things. One is your nitrogen, another is your oxygen in the higher content. So S block elements react with both nitrogen and your oxygen. So in case of group 1, only lithium reacts with nitrogen. Wait a minute. Lithium reacts with nitrogen, but not in the room temperature, but not in the room temperature. What happens? Some elements such as lithium, magnesium, calcium, etc. reacts with nitrogen, and nitrogen in the red hot condition, red hot, red hot, red hot condition. This will produce Li3N, lithium nitride, Mg3N2, magnesium nitride, Ca3N2. These are also prepared in the production of ammonia, also calcium nitride. You can give it in water. This will produce you calcium hydroxide plus your ammonia will be the product. So it's very important actually. So lithium in group 1 only lithium reacts with nitrogen. Okay. So rest of the elements generally not undergo the reaction with your nitrogen to form the nitrides. And oxygen, everyone reacts with oxygen. In group 1, everyone react with oxygen, such as lithium form monoxide, sodium form monoxide as well as peroxide. It has a higher stability generally. Okay. KO2, okay, it is superoxide, potassium superoxide, K2O, potassium monoxide, normal oxide, and K2O2, peroxide, okay, peroxide. But the superoxide is more stable. Similarly, RbO2, rubidium superoxide. Similarly, CSO2, they are produced in a higher quantity. So, why this kind of phenomenon occurs? The larger element or members of this group tends to form superoxides due to the uniform charge distribution of the ions of the anions over the large cations. So you should be considered that the superoxides are formed by the larger elements of this family. You can see potassium forms another an abnormal oxide KO3 also. Okay. So you should remember the superoxides are paramagnetic in nature and colorful, but the normal oxides are colorless. So lithium, this kind of property, it is actually stable in nature due to the polarization. So these are the oxide. Then we'll see the carbonates and bicarbonates. Actually, all of them produce carbonates here. Wait a minute. Okay. Sorry for the interruption. All of them, all of them produces carbonates. This topic is most important actually. You can see Li2CO3, K2CO3, sorry, Na2CO3, sodium carbonate. This is also known as soda ash, Rb2CO3, and CS2CO3. Similarly, here BeCO3, MgCO3, CaCO3, SrCO3, BaCO3. Always remember the thermal stability of the carbonates increases going down the group, because you can see here CS2CO3 is greater than Rb2CO3 is greater than K2CO3 is greater than Na2CO3 is greater than Li2CO3 because because these are, while going from top to bottom, the ionic nature increases as it has very high melting point. But this Li2CO3, you can write down here, Li2CO3 undergo decomposition easily when heated to produce Li2O. Okay, lithium oxide. Actually, this is stable. This kind of phenomenon is because we'll discuss it about is in our in later. Okay, this kind of phenomenon is because lithium has a smaller size, so it polarizes the electron out of the oxygen, and the carbon dioxide is released during the process. This kind of this reason, while going from top to bottom, the ionic nature increases. It can also be you can also apply it in the nitrates also, though the nitrates are highly soluble in nature. Nitrates, these are highly soluble in nature. So the thermal stability of the nitrates CsNO3 is greater than, this is known as Indian saltpeter, NaNO3, chili saltpeter, than your LiNO3. The problem is that this also behaves differently because these nitrates, all the nitrates in group 1 produces nitrites, but LiNO3 when heated produces lithium oxide. Okay, this produces lithium oxide, and nitrogen dioxide is evolved during the process. So you should remember the nitrates also behaves like the same thermal stability and same reason actually. Bicarbonates are also like that. CsHCO3 greater than RbHCO3 greater than KsHCO3 greater than NaHCO3 greater than LiHCO3. This is attributed to the fact that while going from top to bottom, the electropositivity of the atom or the group 1 elements increases. As the electropositivity increases, the ionic nature also increases, and they will have a high amount of melting and boiling points. Okay, so you should remember the carbonates and bicarbonates, the while going from top to bottom, the thermal stability increases continuously, but lithium always behaves differently due to its smaller size, high IP, and high ionization potential, and higher electronegativity compared to the rest of the elements present in that group. Okay, next we'll see here. Wait. Okay, next we'll see about your halides. Okay, now you'll see the halides. All of them, all of the members, all the members in group 1 produces halides. Such the reactivity increases while going down the group, and you should remember the reactivity of fluorine is greater than chlorine is greater than sorry, bromine, and iodine. And the tendency to form halides goes on increasing while going from top to bottom. You should remember, lithium produces sorry, lithium produces partially covalent halides such as you can see LiCl, NaCl, ACl. The solubility is like that. This is because lithium has the smallest size. Lithium has the smallest size and higher polarizing power. Fazan's rule, you should remember. Sorry. You should remember the Fazan's rule. Lithium is smaller in size, so it has a very high polarizing power. As the polarizing power is high, the covalency is also high. Covalent nature is also high, and the covalent nature is very high. That's why it has lesser amount of solubility in water, except LiF insoluble in water. So this is the trend of the halides. Now we have almost covered the physical properties of this group. Now we'll see physical and chemical properties, some chemical properties of the group. Now we'll see the anomalous behavior of lithium. Or abnormal behavior of lithium, you can write down here. Number 1 point, it is not affected by air. Number 2, it does not tarnishes like the other metals in group 1. Number 3, it is lightest and stored under paraffin. Number 4, it does not lose its metallic luster when exposed to air. Number 5, it does not react with cold water below 273 Kelvin. Number 6, it reacts mildly with water but rest of the elements reacts violently with water. Number 7, it forms normal oxide and no peroxide or superoxide. Next, number 8, okay, in group 1, it is the only one which can form carbides. Number 9, in group 1, it can form nitrides, but rest of them can't. Number 10, lithium halides have partial covalent characters due to its high polarization power. Number 11, lithium can form hydrated halides such as LiCl.2H2O, but the remaining members produces anhydrous halides. Number 12, lithium nitrate or LiNO3, when heated, produce lithium oxide, but rest of the elements produce nitrites. Number 13, all the members can produce amides. Only lithium can form imides. Number 14, all the carbonates have very high decomposition temperature, but only lithium has low decomposition temperature and produces your lithium oxide. So I think this will be enough for your board and entrance examination or your etc. Okay, so this will be enough information for lithium, anomalous properties of lithium, which is actually very important. Okay, so these are the points which you should remember. Okay, it is the anomalous properties of your lithium. Now we should see an abnormal phenomenon of a diagonal relationship. You should see the properties similarities between the lithium and magnesium. This is known as a diagonal relationship. Diagonal relationship. Okay, what happens? Why diagonal relationship? You can see in the periodic table, lithium is present here, sodium is present here, magnesium is present here. So you can see lithium and magnesium are present in the diagonally. Similarly, beryllium and aluminium is also present diagonally. Okay, now you can see beryllium, aluminium is present in also diagonally. You can see there are some similarities with these elements. Why? Because you can see while going from lithium to sodium, size increases. But while going from left to right, size decreases. So what happens? These sizes becomes identical and their electronegativity sizes becomes identical. So their size, electronegativity, density, electrode potential, flame colorization, they both undergo, that does not undergo flame test. Flame colorization don't undergo, they does not undergo flame colorization, etc. Or you can see density, electronegativity, we have write down. So they becomes same. So these are the, this is the reason between the diagonal relationship of the diagonal relationship. This is because the size increase while going from top to bottom is cancelled or quenched by the decrease in size while going from top to bottom in the periodic table. Okay, that's why lithium and magnesium has similar sizes, and that's why they can show the diagonal relationship. Almost their physical and chemical properties are same. We can see here lithium can form nitrides, magnesium also, such as Li plus N2, red hot, produces Li3N, Mg plus N2, red hot, Mg3N2. First point. Number two, lithium carbonate and magnesium carbonate both give oxides during heating, such as Li2CO3. This will give you Li2O plus CO2. Magnesium carbonate, MgCO3, this will also give you magnesium oxide. Number three, their electronegativities are also similar. Next, you can see here, wait for some time. Again, we can see the nitrates of both lithium and magnesium on heating gives us oxides, such as you can see while LiNO3 is heated and MgNO3 whole 2 is heated, both of gives them gives Li2O, and this will give your MgO. Next, you can see both lithium and magnesium compounds are soluble in pyridine or alcohol medium due to their covalent nature. Next, you can see their reactions with sulfides are also same. So these are some of the properties of your diagonal relationship of lithium and magnesium. Rest of the points are also present, so they are not generally necessary. So today we have covered these topics. In our offline classes we have also covered up to this one. That's why I am ending this video here, because we have to complete the same amount of part in the offline, as well as in the online. So those students which are not, who are not coming in your offline classes, this video is for them. In our offline classes, we are doing it in a better way. Okay, we writing the notes also. That's are also important, because some important points, those we will, you will forget about this in the later stages. That's why this is very important to note it down, everything that I have told you here. Actually, is a detailed explanation video. We are not going to the shortcuts here. Okay, because if you are wanting to do good results, you have to know the details, then you should do the shortcut. After you know the details, then you should do the shortcuts. Without knowing the details, if you do the shortcuts, then you will be a very bad phenomenon, or the result will be not very good. So it is very important to understand what is the reason and the explanation between the phenomenon that are happening in the group one. So that's why we should first see the details, then we will see the rest of the parts. Okay. So I'm ending this video here. If you are comfortable with the way that I'm giving you the lectures, you can subscribe my channel. Actually, I'm not uploading regular videos in my classes. We are actually giving the unlisted videos. So after a very long time, I am posting this video YouTube um, for everyone. Okay, so if you are satisfied with the video, and you should give me a like and subscribe the channel also. So thank you all for watching, and have a nice day.